Modern cybersecurity functions as a complex, moving mechanical system. The traditional concept of a static stone wall is obsolete. Defense is now defined by the continuous, active management of risk. This is a perpetual loop. It requires defenders to protect digital assets while simultaneously monitoring for the inevitable probes that target them. The loop starts with protect, deploying controls against compromise, and detect, flagging suspicious behavior. It feeds into respond, limiting damage, and recover, safely restoring operations. Under pressure, if threats bypass initial protection, survival depends on active nodes isolating the anomaly before escalation. Perfect safety is a mathematical impossibility. Cybersecurity is the engineering of operational resilience under continuous, predictable pressure. The CIA triad ensures security. Confidentiality uses encryption to block unauthorized access. Integrity calculates cryptographic hashes to prove data remains unaltered. Availability engineers redundant infrastructure, rerouting blocked pathways. Finally, authentication and authorization verify identity, while non-repudiation provides immutable cryptographic proof of actions. Every cyber attack is an attempt to collapse one of these 5 specific pillars. Every defense is an attempt to reinforce them. Digital defense is asymmetrical. Defenders must secure every possible entry point and user behavior, while an attacker only needs to locate one single flaw to breach the network. To exploit those flaws, adversaries deploy specific threat vectors. Malware is malicious software engineered to compromise devices, steal data, or establish persistent remote control over a target. Phishing targets human psychology. It uses deception to trick employees into sharing their credentials, bypassing technical controls by manipulating the person behind the screen. Ransomware is an extortion attack. It specifically targets the availability pillar, encrypting critical data and halting business operations until a payment is made. Finally, the insider threat occurs when a user with legitimate access misuses those privileges. This can be intentional sabotage or simple negligence, such as losing a device or misconfiguring a database. Advanced adversaries rarely rely on a single method. They string these vectors together into a calculated sequence to dismantle a target's architecture. We can observe how these threats cascade by mapping a standard enterprise breach. This timeline details the 5 steps an attacker takes to move from initial contact to total system compromise. It begins with the initial hook. An attacker sends a carefully crafted phishing email that looks like an urgent IT update, slipping past automated filters to land in an employee's inbox. This leads to step 2, credential exposure. The employee enters their login details into a fake portal, unwittingly granting the adversary the specific authorization tokens required to bypass the authentication pillar. At step 3, the attacker leverages that unauthorized access to abuse system privileges. They install malicious tools and move laterally across the network to locate high-value data. The attack culminates at step 4, ransom impact. The deployed malware locks the data, destroying system availability and halting the organization's ability to function. Security engineering requires dissecting this timeline to learn precisely where to break the chain. Defenders cannot protect a network without intimately understanding this methodology. This brings us to the concept of cross-cutting defenses. These are structural security controls engineered to sever the attack chain at specific vulnerabilities. If an organization enforces multi-factor authentication, or MFA, the chain breaks at step 2. Even if a password is stolen via phishing, the MFA block stops the login process, neutralizing the credential exposure. Similarly, strict network segmentation and routine patching intercept step 3. By fixing known software flaws and isolating sensitive servers, the architecture blocks lateral movement and privilege abuse. Effective cybersecurity requires placing strategic roadblocks deep inside the network. This ensures that a localized failure does not result in a total compromise. Theoretical architecture must be subjected to real-world stress. This is the operational role of the ethical hacker, to proactively assault these defense blocks and validate their effectiveness before a hostile actor can. As security technologist Bruce Schneier noted, this work requires a specific mindset. Ethical hackers treat every test as a chance to improve. This testing takes 2 forms. On the left, vulnerability assessment. a broad radar sweep cataloging known weaknesses. On the right, penetration testing, an aggressive red line charting a specific path to prove how much damage an adversary could inflict. Assessments map the theoretical risks of a network. Penetration testing proves the empirical reality of what an attacker can achieve. This infographic outlines the boundary between professional testing and cybercrime. Legal authorization. Ethical hacking requires formal permission. Every legitimate engagement is governed by rules of engagement and a defined scope, dictating exactly what systems can be touched and forbidden methods. Testers are also bound by ethical obligations. Data minimization requires them to access only the precise data needed to validate an exploit, while responsible disclosure mandates that all findings are reported directly to the organization. Professionalism in this field is defined by working strictly inside these boundaries. Stepping outside the authorized scope constitutes an operational and legal failure. The primary output of an ethical hack is actionable intelligence. This documentation provides the technical context required to harden the organization's defenses. A professional tester translates complex exploits into specific remediation steps. They provide engineering teams with the exact configuration changes required to close gaps. Looking back at our CIA triad, those remediations act as structural reinforcements. Applying these patches directly hardens the data boundaries, ensuring the organization meets rigorous global compliance standards like NIST and ISO 27001. The ethical hacker identifies specific cracks in the system, creating a blueprint for resilience. Every discovery builds a defensible architecture, capable of withstanding continuous pressure.